Hello, calculus fans. Okay, so we're here with another problem. We want to find all points on the curve y equals 9x over x squared plus 9, where the tangent line is horizontal. Well, let's take a look at the graph of this thing. You might want to try looking at a graph on your calculator too. Okay, so here's what this thing looks like. And so we're trying to find the points where the tangent line is horizontal. Now it looks to me like there's a couple of places. There's one here, there's a horizontal tangent line. There's another one down there. Okay, so we're going to try to find the x values and the y values of those points because we want all points, so that means to find x and y values. All right, so just based on looking at the picture, it looks like there's 2 points where the tangent line is horizontal. It also looks like those 2 points are mirror images through the origin. And actually, this makes sense because the function that we're starting with is an odd function. Well, let me remind you what it means for a function to be odd. So remember that the definition of an odd function is one that satisfies f of negative x is equal to negative f of x. Now we can verify this in the original function by plugging in a negative x in place of x, and if we do that, then the x that's on the inside of the x squared disappears, but this negative gets pulled out in front, and so we end up with that f of negative x is in fact equal to negative f of x. And so that means the function is odd. And I would say for our purposes, the main thing that you want to remember about odd functions is that their graphs are symmetric about the origin. And so if we're going to expect a tangent line that is horizontal in the first quadrant, we should get a corresponding point in the third quadrant where it also has a horizontal tangent line. So it makes sense that we're going to expect those 2 points like that. All right, I'd like to go back to the original function and compute a derivative. We can use the quotient rule. So we get low d high minus high d low, square the bottom, and away we go. Make sure you check to see in the original expression, the original function, which pieces is high, which piece is low, and how that fits in with the rhyme for the quotient rule. Low d high minus high d low, square the bottom, and away we go. Okay, so let's do a little simplification now. So if we distribute the 9, we'll get 9x squared plus 81, and then the 9x times 2x turns into 18x squared, still with the minus sign in front of the 18. Now let's simplify a little. So after we simplify, we'll get 81 minus 9x squared over x squared plus 9 quantity squared. So this is our derivative, and we're trying to see where the tangent line is horizontal, so we want this derivative to equal 0. Okay, so we want the tangent line to be horizontal. We're setting this derivative equal to 0, and we're going to solve for x. So there we've set it equal to 0. We can go ahead and multiply both sides by x squared plus 9 quantity squared, because that piece is never going to be 0, so it's okay to multiply everything by that. So we'll get 81 minus 9x squared. Let's get rid of a 9. We'll divide both sides by 9. And so we end up with 9 minus x squared equals 0. And then it's pretty easy to see. X has to be equal to plus or minus 3. So those are going to be the x values where the tangent line is horizontal. We also need the y values at those points. So let's plug positive 3 and negative 3 back into the original function. We're plugging negative 3 and positive 3 back in the original function because we need to know the corresponding y values. So here if we plug in 3 back into the original function, you can see that this all works out to be 3 over 2. So that's the y coordinate associated with 3. And then if we plug in negative 3, and you can work out what we get here, we end up with negative 3 halves. So that's the y coordinate with corresponding to the point where x is equal to negative 3. So we've got our 2 points. I think the 2 points in question are 3, 3 halves and negative 3, negative 3 halves. And you see, according to our calculations, those 2 points really are symmetric about the origin. So our picture and everything that we thought about it did make sense in the context of our calculations. Okay, that's all for now. So we're looking for points where the tangent line is horizontal, so we're going to set this derivative equal to 0, and we're going to try to solve for x. Alright, so we set this thing equal to 0. We're trying to solve for x here. So we can go ahead and multiply both sides by x squared plus 9 quantity squared, because that expression is never equal to 0, so it's okay to multiply by that. So if we multiply by that, then we end up with 81 minus 9x squared equals 0. We can just get rid of a 9, divide everything by 9, we get this. And now it's pretty easy to solve for x. So we end up with x equals plus or minus 3. So those are the x values where the tangent line to the original curve is horizontal. So we've got the x values. Now we need to get the y values. And we'll get that by plugging in negative 3 and positive 3 back into the original function. So if we plug in 3 back into the original function, we'll get 9 times 3 over 3 squared plus 9. This all works out to 3 halves. You may want to double check the math, make sure it looks good. So that's the y value corresponding to the point where x is equal to 3. We also have negative 3 to plug in, and if we do that, now we'll get a negative 3 halves. And so that's the y value associated with x equals negative 3. So now we've got our 2 points. So the 2 points are 3 comma 3 halves and negative 3 comma negative 3 halves. Notice that those 2 points really are mirror images of each other through the origin. So the symmetry that we talked about at the beginning really bore itself out in the calculations that we made here to get the points where the tangent line was horizontal. Okay, that's all for now.